By the 1960s, the dream of a jet that could take off and land vertically was no longer science fiction. Engineers and militaries around the world were imagining a future where aircraft weren't tied to runways, and the potential implications were staggering. Freeing jets from runways promised to change aviation forever. It could allow aircraft to operate from remote areas, evade attacks on air bases, and deploy in ways that traditional fighters could never match. The British had pioneered the jump jet fighter with the Harrier, proving that vertical takeoff and landing was possible. But Germany had even bigger ambitions. They wanted something unprecedented, the world's first vertical jet lift transport. A plane that combined the speed and range of a jet with more lifting power than almost any helicopter ever built. This wasn't just a fighter. It was designed to move people, equipment, and supplies across the battlefield, redefining how an air force could operate. Yet creating a VTOL aircraft, vertical takeoff and landing, was one of aviation's greatest technical challenges. Unlike conventional aircraft, which rely on airflow over wings to generate lift, a VTOL jet must rise vertically using engine thrust alone. Without forward motion, the wings are essentially useless. That meant every pound of weight, every aerodynamic choice, and every engine had to be carefully calculated to produce enough lift to rise off the ground. But vertical lift was only part of the problem. Engineers also had to keep the aircraft stable while hovering. Conventional control surfaces, ailerons, rudders, elevators, rely on air moving past the plane to be effective. In a hover, with no forward speed, they do almost nothing. The jet had to rely entirely on engine thrust, not just to lift, but to maintain orientation and balance in mid-air. And, once airborne, the jet still needed to transition seamlessly into normal flight, cruising at high speeds like a conventional aircraft. Several engineering solutions were proposed. One approach used dedicated lift jets for vertical takeoff, with a separate engine powering forward flight. Another aimed for a single engine capable of vectored thrust that could be redirected downward for lift or backward for forward motion. A third combined both ideas: lift jets for takeoff and landing, paired with vectored main engines for flight. Each of these approaches brought its own challenges, from engine complexity to stability control, and each pushed the boundaries of 1960s technology. Throughout the 1960s, countries like Britain, the United States, and Germany invested heavily in VTOL development. The strategic advantages were clear. In World War II, fighters could take off from virtually any flat field, often just a few hundred feet long. But jet aircraft of the Cold War era required thousands of feet of concrete runway to reach takeoff speed. That made them extremely vulnerable in the opening hours of a conflict. Runways were obvious targets, and their destruction could ground an entire air force in minutes. For West Germany, this vulnerability was particularly acute. The country's air bases were just a few hundred kilometers from the borders of the Soviet bloc, putting them within easy striking distance of enemy aircraft and cruise missiles. VTOL aircraft could operate without runways, allowing planes to be dispersed across forests, hidden inside hangars, or even staged on the country's extensive highway network. In theory, it offered unprecedented operational flexibility and survivability. In 1960, West Germany began building an air force around VTOL technology. Initial projects focused on supersonic fighters with pivoting wingtip engines, followed by VTOL strike fighters for ground attack roles. But a critical component of this vision was a VTOL transport aircraft, a plane capable of delivering troops, supplies, and equipment directly to forward bases, often in remote or improvised locations. That plane would have to combine vertical lift with jet speed, carrying more weight than any conventional helicopter, and doing so safely and reliably. By 1962, West German aircraft manufacturer Dornier was assigned the enormous challenge of developing this aircraft. Engineers faced the monumental task of designing everything from scratch: engines, flight control systems, avionics, and airframe. The Do-31 was born, a plane unlike anything the world had ever seen. The Dornier Do-31 used 2 vectored thrust turbofans for forward flight and 8 lift jets embedded in its wingtip pods for vertical takeoff and landing. Together, these engines generated a staggering 66,000 pounds of thrust, more than almost any helicopter ever built. Yet it wasn't just raw power that made the Do-31 special. Its lift jets had to work in perfect harmony with a complex hybrid flight control system. A part digital, part analog computer that managed stability during hover, compensated for wind, and ensured a smooth transition into forward flight. In normal flight, the lift jets could be shut down, allowing the Do-31 to cruise at speeds exceeding 700 kilometers per hour. It could carry 36 fully equipped troops, or nearly 6 tons of cargo, over impressive distances. The combination of speed, range, and vertical lift capacity was unprecedented. In theory, the Do-31 could operate from almost anywhere, providing logistical support to dispersed VTOL fighters and revolutionizing military operations. Development was grueling. The sheer number of engines, the novelty of vertical lift, and the limitations of 1960s technology meant progress was slow and costly. Over nearly 5 years, Dornier engineers refined the aircraft's systems, conducting extensive ground and flight testing. By 1967, the Do-31 was proving its capabilities, stable in hover, agile in forward flight, and ready to demonstrate its potential. Some even imagined VTOL airliners operating from rooftops or helipads, though such ideas remained decades away from practical reality. Yet despite its promise, the Do-31 faced harsh realities. By the late 1960s, strategic priorities shifted. The immediate threat of all-out conflict with the Soviet Union seemed less likely, and the enormous costs and technical risks of VTOL development made the program increasingly difficult to justify. The jet's complexity was staggering. 10 engines, extensive fuel requirements, and sophisticated control systems made it heavy, expensive, and maintenance-intensive. Noise alone would have ruled out most civilian applications. Attempts to showcase the Do-31's capabilities, including a high-profile demonstration at the 1969 Paris Air Show alongside Britain's Harrier, drew attention but little concrete interest. Without development partners or buyers, Dornier was forced to cancel the project in 1970. The VTOL strike fighters it was designed to support would ultimately suffer a similar fate. And like many VTOL projects of the 1950s and 60s, the Do-31 became a remarkable but unrealized vision of what might have been. Still, the Do-31 remains a testament to the ingenuity and ambition of its era. It was a machine that pushed the boundaries of what was technically possible, attempting to combine jet speed, helicopter versatility, and operational flexibility. Its legacy is not just in what it achieved, but in the lessons it offered for aviation engineering, flight control systems, and the future of vertical lift technology. Decades earlier, Japanese engineers had pursued equally audacious concepts, including underwater aircraft carriers that combined the stealth of a submarine with the strike capabilities of an aircraft carrier. The post-war period was full of such visionary experiments, each attempting to solve strategic problems in innovative ways. The Do-31, in this context, was part of a larger story of human ingenuity, a time when engineers dared to imagine aircraft that could fly differently, fight differently, and support military operations in ways previously thought impossible. Though VTOL jets would not revolutionize commercial aviation in the 1960s or 70s, the ideas tested by the Do-31 would influence future designs. From the Harrier jump jet to modern tiltrotor aircraft, the principles explored in West Germany's ambitious VTOL program continue to inform aerospace engineering today. The Dornier Do-31, while never entering service, remains a striking example of ambition meeting technological frontier. A reminder that innovation often requires pushing beyond what seems possible, even if the world isn't quite ready to follow.